welcome to The Explainer. If you're a student, especially in a field like psychology, that word hypothesis can sound a little intimidating. But I promise you, by the end of this, it's going to be one of the most powerful tools in your research kit. So let's jump in and crack the code. Okay, so let's start with a really common situation for any researcher. You see something out in the world that's just fascinating, and it sparks a question in your mind. But now what? How do you take that spark of curiosity and turn it into something you can actually, scientifically test? Well, that bridge you need to build, that's the hypothesis. And as you can see from this little roadmap here, it is the absolute critical link that turns a vague question into a real plan. It connects your big idea to the data you're going to collect, the tests you'll run, and the conclusion you'll eventually reach. It gives your whole project a laser focus. To put it really simply, a hypothesis is just a precise, testable statement about what you expect to find. And look, it's not a wild guess in the dark. It's an educated prediction, something you come up with based on a theory you've read or maybe some previous research. Your entire study, from start to finish, is designed to see if the evidence you gather supports this prediction or challenges it. All right, let's get into the nitty-gritty because this is important. A research hypothesis never, ever works alone. To really test an idea properly, you have to frame it as a kind of showdown between two completely opposite statements. So, on one side of the ring, you've got the null hypothesis. We call it H0. Think of this as the boring status quo position. It basically says nothing interesting is happening here. No effect, no difference, no change. And on the other side, you have the alternative hypothesis, or H1. Now, this is your actual prediction. This is the one that says, hey, wait a minute. I think an effect does exist. Let's make it concrete. Say you're looking into whether there's a gender pay gap. The null hypothesis would state that, nope, on average, the salary of men and women does not differ. The alternative hypothesis, which is probably what you're interested in testing, would say, yes, their salaries do differ. Your job as the researcher is to collect the data and see if you have enough evidence to confidently reject that no difference claim. This image just illustrates that idea perfectly. It's like you're looking at two parallel universes. In the null hypothesis universe on the left, everything stays the same. There's no effect. But in the alternative hypothesis universe on the right, something has happened to cause a real, measurable change. And our job is to figure out which of these two worlds our data actually belongs in. Okay, so now that we've got that down, let's build on it a little. Because it turns out not all hypotheses are created equal. We can actually categorize them based on the specific kind of question we're trying to answer. The first big choice you have to make is this. Are you looking for a difference between groups or a correlation between variables? A difference hypothesis is pretty straightforward. You're comparing two or more separate groups, like testing a new drug on a patient group versus a placebo group. A correlation hypothesis is different. It's looking for a relationship, an association between two things that you can measure, like asking, as people get taller, does their weight also tend to increase? And you can really see the distinction in these visuals, right? On the left, we're comparing separate buckets of people. On the right, we're plotting a bunch of dots on a graph and looking for a trend. And this choice you make here is absolutely critical because it completely changes the kind of statistics you're going to use later on. Okay, the next layer of distinction is all about how specific you want to be. Are you just predicting that something will happen, or are you predicting the exact direction it'll go in? A non-directional or two-sided hypothesis is kind of open-ended. It just says salaries differ. But a directional or one-sided hypothesis, that makes a much bolder claim. It says men earn more than women. See the difference? This choice has a direct impact on your actual statistical test. Just like this slide shows, a two-sided test is looking for a surprisingly high or a surprisingly low result. But with a one-sided test, you're basically putting all your statistical eggs in one basket. You're telling the test, hey, only look for an effect in this one specific direction I predicted. It's a riskier but potentially more powerful bet. So, you've carefully built your null and your alternative hypotheses. You've decided if they're about differences or correlations, and if they're directional or not. Now, for the moment of truth, how do we actually use our data to make the call? Well, that's where the logic of hypothesis testing comes in. The very first thing we have to do before we even collect a single piece of data is set the rules of the game. We have to set our standard of evidence. This is called the level of significance, or alpha. And what it really is the amount of risk we're willing to take of making a very specific mistake. the risk of concluding there's an effect when actually there isn't one. It's our line in the sand for what we'll consider unlikely enough to be a real finding. In psychology, and honestly most sciences, the universal golden rule for this threshold is 5%, or as you see it written here, 0.05. What this means is that we, as a scientific community, have basically agreed that we're willing to accept a 5% chance of crying wolf, of saying an effect is real when it was actually just a fluke of random chance. Once that rule is set, the decision process is actually super simple. First, your statistical test crunches your data and spits out one number, a p-value. Now that p-value is everything. It's the probability that you would get results like yours if the null hypothesis of no effect were actually true. So if that probability is really, really small, less than our 0.05 line in the sand, we say, wow, that's too unlikely to be chance. We reject the null hypothesis and say our result is statistically significant. But, and this is a big but, whenever you're making decisions based on probability, there is always a chance you'll get it wrong, and it is absolutely essential to understand the two different ways we can mess up. This grid is awesome. It lays out the 4 possible outcomes perfectly. See, in the real world, the null hypothesis is either true or it's false. And based on our data, we either reject it or we don't. 2 of those boxes are correct decisions, hooray, but those other 2, well, those are the errors we're always trying to avoid. Let's break those down. A type 1 error is a false positive. It's a false alarm. It's when we get all excited and say we found an effect, when in reality it was just random noise. A type 2 error is the opposite. It's a false negative. It's a missed opportunity. A real effect was actually there, but our study just wasn't sensitive enough to pick it up. And this brings us to probably one of the most important lessons in all of statistics. Getting a statistically significant result is only half the story. Your p-value, your significance test, it just gives you a simple yes or no answer to the question, did we find an effect? But effect size asks a much more important question. Okay, but how big is that effect? This right here is something you should probably write down. It is a vital takeaway. If you have a huge, massive sample size, even the tiniest, most trivial, completely meaningless difference can become statistically significant. A p-value on its own can be so misleading. You have to look at both significance and effect size to understand if your finding actually matters in the real world. And that really leaves us with our final thought, doesn't it? Science isn't about finding absolute 100% certain proof. It's a process of building evidence piece by piece. A hypothesis test doesn't prove that you're right. It just tells you that the evidence you've collected seems to be on your side. And understanding the limits of our own tools, well, that's what makes for a truly great researcher. It's a question we all have to keep asking ourselves.